Hello, I'm glad to introduce our new work, Matching Primitives, Shapes Abstraction from Signed Distance Function. Representing complex objects with basic geometric primitives has long been a topic in computer vision. Primitive-based representations have the merits of compactness and computational efficiency in higher-level tasks such as physics simulation, collision checking, and robotic manipulation. Unlike previous work which extract meshes from a signed distance function, we present a novel method named matching primitives to obtain a primitive-based abstraction directly from an SDF. In this paper, we focus on a versatile geometric primitive called superconjugates to represent scenes. A superconjugate with a general pose is only encoded by 11 parameters. More importantly, superconjugates have closed-form Minkowski sum, making it an efficient representation for collision detection and motion planning. Our goal is to approximate a target shape encoded in an SDF with a combination of geometric primitives. To solve this problem, we need to answer two questions. What is the set of voxels where geometric primitives can be extracted, and what geometry best fit the underlying set of voxels? This is a chicken and egg problem. The answer to either of the problems will lead to the answer to the other one. For example, if we know the parameter of a geometric primitive, we are ready to tell its corresponding underlying voxels. Similarly, if we are given a set of voxels which encodes a geometric primitive, we can easily solve the parameter with the least square method.
To tackle this problem, we propose a two-step probabilistic approach. For better illustration, we use a 2D case as an example. First, we check the connectivity of voxels at different levels of signed distances. Given the target SDF, our algorithm checks the connectivity of voxels whose signed distance is less than a sequence of thresholds. Each threshold defines a set of disjoint isosurfaces encompassing the connected voxels whose signed distances are less than the threshold. We start from the innermost signed distance and continue marching on the sequence until a region which is large enough to extract geometric information appears. Each of the connected regions is an ideal starting point for growing a primitive. This is because, first, those volumes are among the most interior of the target SDF, corresponding to the most prominent part of the geometry. Second, disconnected and weakly connected volumes can be separated apart. Third, the SDF of a primitive can also be interpreted as layers of isosurfaces and thus sharing similar geometric structure. And furthermore, the size of the volumes is large enough to provide sufficient geometric information for the primitive recovery. Next, for each of the volume of interest, we initialize a geometric primitive as a circle. We march on the scope of voxels from which a primitive is able to be extracted in a probabilistic sense, and simultaneously solve for the parameters of the primitive to capture the underlying local geometry. That is, we model the signed distances of voxels as observations generated from a probabilistic distribution. A voxel can either contribute to the current geometric primitive or be discarded as an outlier. Given the current estimation of the primitive, we are able to establish the probabilistic correspondences between the voxels and the geometric primitive from a posterior perspective via the Bayes rule. And then, the parameters of the geometric primitive is updated according to the estimated probabilistic correspondences. The two steps alternate until convergence, similar to the EM algorithm. We can see that the upper half of the human shape is captured in the first round. Again, we conduct the connectivity marching on the remaining region. Then a primitive is initialized and marches to capture the shape of the right leg. Finally, the region and shape of the left leg is detected and recovered. Combining all the primitives, we are able to approximate the target shape accurately. Here is the visualization of the 3D case. The pose and shape of the chair is approximated with only 18 supercortics, which can be fully represented with very few numbers as shown on the right-hand side. The abstraction only occupies less than 1 kilobyte. We evaluate our algorithm on the ShapeNet dataset. Our algorithm is able to describe objects accurately without training, and inherently generalizable among different categories. Our method achieves the state-of-the-art in shape abstraction, outperforming the existing methods by a large margin. Our method can successfully separate different parts if they possess different geometric semantics. For example, telling apart cuboids, cylinders, and ellipsoids. Therefore, it is semantically interpretable. In many cases, the segmentation coincides with the human-defined semantics, even though it is not chained to. Here are more examples of our primitive-based abstractions comparing with the meshes generated from the same SDF with matching cubes. Our representation is compact, about 1,000 times smaller than the meshes, but still captures the key shapes of the object vividly. Our code is open source. Please scan the QR code to find out more. Thanks for watching our video.